Oh yeah, here we go. You're about to learn how to find Riemann sums and a trapezoidal approximation when given tables of data. So here we're not actually given the function as like x squared or root x. We're just given spots of values. So let's read the problem. And we're going to do this in several different ways, all with the same prompt. The table of values below are for the velocity v of t of a freakishly fast ostrich, measured in meters per second. Use 5 equal, so I'm going to underline that, 5 equal subintervals and a left Riemann sum to approximate the total displacement of the ostrich on the time interval from 0 to 15. So that ostrich is running back and forth, imagine on a straight track. Let's talk about why even finding the Riemann sum would find displacement. If you think about what displacement is, that's going to be the areas of each rectangle between a curve and an axis. So let's just say that this describes velocity. It's not what this curve actually looks like. If you take rectangles and you find the areas of each of them, it's going to approximate the area between the curve, right, and the x-axis, this little section right here. So let's look at one rectangle real close. This change right here, this would be the x-axis or the t-axis. That would be a change in time. And this right here would be the velocity at some time. And if you multiply velocity times time, a small change in time, you're going to get a very small displacement. How far you go from the start to finish. So for instance, if you're going -3 miles per hour and you multiply that by 2 seconds, or 2 hours, I guess, then you will have gone -6 miles over that time. Or if it's 10 meters per second and you travel for 2 seconds, 10 times 2, rate times time, gives you 20 meters. So that's how displacement works its way into this. So that's why we want to use the Riemann sum to find displacement. We're going to approximate the area between the curve, v of t, and the t-axis. All right, so now let's get into the problem here. It's actually not so bad. What I like to do when I'm given a table of data is I want to find my subintervals first. So I know that we're going to be going from 0 to 15 seconds. So overall, what I imagine is I've got like some number line, and I go from 0 to 15, so it's 0 to 3, here we go, to 6, to 9, to 12, and then on to 15, and I know that we got 18 at the end of this. And then on each of these, I don't have to even imagine. I just know that I've got rectangles going up off of these. And what we want is a left-hand approximation. So you're getting values from the left-hand part, from 0, 3, 6, and so on and so forth. So in terms of finding the areas of each of these things, I need delta t, right, the width of each rectangle. That's going to be from here to here, and here to here, and here to here, here to here, and here to here. And I need the heights. But in this case, I need the heights at the left endpoint. Okay, well, in this case, that would be v of 0. That would be the left endpoint on the first interval times delta t. Plus, then I would need 3 to 6. That interval, the left endpoint, v of 3 times delta t. Then I need this left endpoint, plus v of 6 times delta t, plus v of 9 times delta t, plus v of 12 times delta t. So we're on this interval here, 0 to 3, 3 to 6, that's 2 intervals, 6 to 9, 3, 9 to 12, 4, 12 to 15, 5, and we're picking each of the left endpoints each time. So just imagine going endpoint to endpoint, left one, 3 to 6, 3, 6 to 9, 6. That's how we choose those values. Now notice that delta t is the same in all of these. It's 3 every single time. Every single time. So I'm going to factor this delta t out when I go to find my value. So that's going to be 3 times v of 0. How do I find that? Right from the table. So that's going to be 40 plus v of 3, 30, right from the table, plus v of 6, 70, plus v of 9, 80, not bad, plus v of 12, 61. And on an advanced test like the AB or the BC exam, this is your final answer. This is considered numerical. Don't simplify it. Now, what are your units? Well, the ostrich was going in meters per second. Time was in seconds, so seconds, meters per second. When we multiply seconds times meters per second, you get meters. This is in seconds, meters per second, so we get seconds. That's it. And then when you do everything out, you're going to get 3 times this entire quantity here, which I'll come back to you in a second with. And after some shoddy video editing, here we go. What we've done is we've added all these up. multiplied by 3, and we get 843, and the units are in meters. I wrote down seconds, but seconds times meters per second obviously gives you meters, so my mistake there. Okay, that's all for this one. We're going to now carry on and we're going to find a right hand, a midpoint, and a trapezoidal approximation, all with the same data, just so that you can see there's not much of a difference. And we'll take a little less time doing the next few ones. Nice job on that one. We just approximated the area between the v of t curve and the t curve, which gave us an approximate displacement of the ostrich. So the displacement being the ending value of position minus the starting value. Okay, the table of values below are for that same freakishly fast ostrich. We have again 5 equal subintervals, and we're going to approximate displacement using a right Riemann sum from 0 to 15. So a right sum, so look at your subintervals. If we have 0 to 15, we're going to go from here to here, and we have 5 subintervals. So that would be 0 to 3, 3 to 6, 6 to 9, 9 to 12, and 12 to 15. So on each of those, again, what we're doing is we're going to find v of t times delta t. That gives us the area of a rectangle. In each subinterval, we are now taking the right endpoint because we want the right Riemann sum. So our displacement is approximately then going to be, in this case, v of 3. That would be the right-hand part. So that's v of 3 times still 3, because delta t is still from 0 to 3. You don't change the interval. The interval's 3 to 6. Okay, so that's going to be plus v of 6 is the right-hand endpoint times 3, because the width is 3. 6 to 9. Well, that's going to be a right-hand point of 9. Still a width of 6 to 9, which is 3. Area of rectangles coming up at you. Next one, right-hand endpoint from 9 to 12, v of 12. Times 3, that's the width. Plus v of 15, because 12 to 15 is still the same interval, and that right-hand part would be v of 15 times 3. So we can factor out that 3 from everything because it's in every term, and now just plug in the numbers that each of these represent, being careful to select the proper data. v of 3 is 30, v of 6 is 70, nice, v of 9 is 80, v of 12 is 61, and then v of 15 is 50. And I'm going to pause the video right here. We got our units of meters, of course. On the AB or BC exam, leave your answer unsimplified. That's numerical. This is not numerical. This is fine, but a lot of teachers want you to simplify. I'm going to pause the video and magically come back with an answer. It won't pause on your end, though. See the magic in a second. Bam! Look at that. The answer's there out of nowhere. So we've got 3 times this sum to 291, which is 873 meters. The left-hand sum was 843 meters. So we don't know whether one's an under and overshot because we don't know if the curve's going up or down the whole time. But we know that these values are estimating the displacement of that freakishly fast ostrich. So what's coming up next? We did a left hand, we did a right hand, same exact problem, midpoint Riemann sum, but here we're doing 0 to 18. Use 3 equal subintervals, as indicated by the data here. So again, we still have seconds, we still have meters per second, and if I multiply seconds times meters per second, I get meters. Now, we have different subintervals. We have 3 subintervals from 0 to 18. So let's break them up. So 0 to 6 is going to be here to here. 6 to 12, that's a second subinterval, and 12 to 18. How did I know those are going to be the subintervals? Well, subintervals can never overlap. And we know, because if they do, we might double count values. That's a problem with approximating things accurately. But we know that our whole gap is 0 to 18. So we're literally using this from before. 18 minus 0 is the overall width, divided by 3 rectangles, would give us a delta x of 6. So in this case, it's delta t here. So we've got values of 6 for each of our delta t values. Oh yeah. Now, remember, it's the same thing. You're still finding the height of the rectangle represented by the velocity, multiplying that by the width of each rectangle, and that'll give you the area of each rectangle, and then we'll add them up to approximate the area between this curve and that axis. All right, so it's the midpoint now that we want. So look on only the interval 0 to 6. Hyperfocus on this. The middle of these two things is at 3, right? So this is the midpoint right here. From 6 to 12, the midpoint is at 9. And then from 12 to 18, 15 is going to be the midpoint. So those are the 3 places that we're going to find our midpoint values. So we've got v of 3 The width now is not 3 as it was in the previous problems. It would be an overall width of 6 plus 6 to 12. V of 9 is our midpoint. Times a width of 6 plus V of 15 is right in the middle right there times 6. And that is going to give you an approximation. Now that's not numerical, so we'll have to go a little further. So I'm going to take the 6 out. We can factor that out. V of 3 is 30 plus V of 9 is 80. At this point, I'm just pulling the information from the table. V of 15 is 50. And so what we end up with there is 6 times 110 and 50 is 160. And that's going to end up equaling to 960. Remember, our units are in meters. That's it. So that's your midpoint sum. It's all about breaking this down into intervals and then picking apart the information. It's not so bad. You got this. So we got one more to do, right? We haven't done the trapezoidal approximation yet, so of course we're going to do that one to end this video. And I thought let's do it all together in one video so that you can compare them together. The table of values below are for that same ostrich. We're going to use 5 equal subintervals and a trapezoidal sum to approximate the total displacement from 0 to 15. We're still finding the area, but we're not doing V of t times t anymore. Remember that under a curve, with a trapezoid, what you'd have going on there, I'll just kind of draw on a trapezoid, is something like this. So let's pretend this is V of t. This right here and that right there are your bases. So that's B sub 2 and B sub 1. And this overall width is delta t, which is the height. Well, what's B sub 2? It's your second velocity in this interval. So that would be like V of, we'll call it t sub 2. And B sub 1 would be V of t sub 1. What the heck does that mean? It's the opening velocity in an interval. Let's just figure out what our subintervals are. If we're using 5 equal subintervals, then we know we're going from 0 to 15, so let's mark that off. The subintervals will each be 3. 15 is the overall width, divided by 5 is 3. So we're going 0 to 3, 3 to 6, 6 to 9, 9 to 12, 12 to 15. Remember that the area of a trapezoid is equal to 1/2 the height, which the height is delta t, times base 1 plus base 2. Oh, so overall here, what I'm going to do is I'm going to factor out a 1/2 h because we can, right? So I'm going to take out 1/2 times delta t, which is 3 every single time. That's the width of every subinterval. So 1/2 times 3. I factored this completely out because it'll be the same no matter which of the 5 trapezoids we calculate. Then B1 plus B2, well, that's the first trapezoid. That would be V of 0. We're looking at this left endpoint right here in the interval, plus the right endpoint. That's B1 and B2 in this interval. Bam! That's your first trapezoid. Plus the next one. Well, in the next one, let's say that we have a second trapezoid here. That's going to be, I'll just put it right here. Boom. That's not a very good looking trapezoid, but it'll do. B1 in this trapezoid was B2 in the last one. So we start out here. The left endpoint here is 3 plus V of 6. And we're just going to continue with that pattern. The next one will be this and that again. It's always left plus the right endpoints, which would be V of 6 and V of 9. Oh, it's a lot of numbers. And we just continue on with that pattern. I'll go down to this level here, sorry, to make it vertical. V of 9 plus V of 12, left endpoint plus right endpoint. Not bad. Plus left endpoint height plus right endpoint height. V of 12 plus V of 15. All silky now. That's it. So this would still be in meters because you're still finding area. Meters per second times seconds comes out of that. You cannot leave your answer like this even on the A, B, or BC exam. That's not numerical. So what you'd have to do is take all your information from here and plug it in. So this ends up being 3/2 times V of 0 plus V of 3. Literally taking the numbers, it'd be 40 plus 30. And just popping it in for what you see. V of 3 plus V of 6 is 30 plus 60. And you keep going down the road, entering in the values as we see fit. Now, it wasn't plus 60. I marked that one in incorrectly. That was plus 70 right there for 6. Plus, and then we've got 70 plus 80. That was V of 6 plus V of 9. And then V of 9 plus V of 12, which will be 80 plus 61. And then V of 12 plus V of 15, which would be 61 plus 50. That's it. That's your answer if you're taking an AB or BC exam. Now, I'm going to put this on pause on my end. You're going to see magically through the art of editing, the answer will be there. See you in one moment. Bam! Again, through the art of terrible video editing, we've got our answer, 858 meters. That's it. So I'd love for you to watch this video back a couple times just so that you can understand that we're just approximating areas. Look back at the problems and see how we're using these tables and how it's really not so bad. I will see you in the next video. Peace.